So good morning or good afternoon, everyone, and thank you very much for being here. Today we have the pleasure to welcome Professor Jeroen van Hunen from Durham University, and he's going to tell us what we need to build a Craton. And for us, being in Africa, we have quite a few number of Cratons, so we are all keen to hear what he's going to tell us. Jeroen, the floor is yours.
Okay, thank you very much for the invitation and the introduction. So, as Catherine just said, I'm going to talk about how to build Photonic Lithosphere. Now, this talk is kind of divided into two parts. First, I will talk about what a Craton actually is and its key characteristics, because that will be needed to kind of understand the formation of these Cratons. Okay, before I forget, I would like to thank my co-workers. So first of all, I'm going to show quite a few model calculations from Hongliang Wang, who was a PhD student with me several years ago. And he's now a researcher in Oslo. I also would like to thank Graham Pearson, who's a long-term collaborator of mine, and he knows an awful lot about Protonic Lithosphere, and probably without him, this kind of research wouldn't have been possible. He also was at Durham at some point, but now he is in Alberta in Canada. And finally, Charitra Jain, who was a postdoctoral researcher with me until recently, and he now moved to GFZ in Potsdam in Germany. Okay, so first of all, what is a Craton? So there isn't really a fixed definition of what a Craton is. If you go on Wikipedia, you won't find a Craton definition or something like that. But generally, it's considered that Cratonic lithosphere is a lithosphere that has not seen any tectonic activity for at least 1 billion years. And that is kind of described here in the two quotes here at the bottom. Also, Cratonic lithosphere is typically much thicker than other types of continental lithosphere, and this is kind of illustrated in a seismic velocity map here on the top right, which is taken at 150 kilometers depth. So anything that extends to at least 150 kilometers depth is clearly showing up. And the strongest signal comes from the very thickest lithosphere, which is the kind of purple and pink parts of the map, which are almost all Cratonic lithosphere. Not all Cratons are thick. There are a few exceptions like the North China Craton, which recently thinned, but most of them are. And some of them extend to all the way up to 200 or 300 kilometers. Finally, Cratons are generally old. So most Cratonic lithosphere is formed either at the late Archean or the early Proterozoic, so somewhere between 2 and 3 billion years old. So somehow this lithosphere is very stable because it seemed to have survived for at least 2, but in most cases up to 3 billion years, and it's still there today. So key questions most people are asking is, how is it possible that Cratonic lithosphere is able to survive for so much longer than other types of lithosphere, which disappear much more readily? And also, how is it possible that Cratons are so much thicker than other types of lithosphere? So let me first try and address these things. So how is it that Cratons can survive for so long? Well, that's actually not a straightforward answer. There's no clear, easy answer to this, but maybe let me start by asking a simpler question is, how is it possible that continents survive so much longer than oceanic lithosphere? Most of us do know the answer to that, and that has to do with basically the stability of oceanic and continental lithosphere. Oceans have a crust of only 7 or so kilometers, whereas continents have a much thicker crust, and the thicker crust actually gives rise to much larger, much more stability. Sorry, can you still hear me?
Yes,
yes, perfectly.
Because,
yes, we hear you.
because it looks like my computer is kind of frozen. Doesn't seem to respond to anything anymore.
Ah.
I cannot move my cursor or anything. Sorry about that.
No, we don't see any cursor.
No, I don't see any cursor either. And actually, I don't seem to be able to do anything really. My computer seems to be frozen, even though you can still hear me, apparently.
Yes, we can.
That's interesting. Okay. I don't know what to do about this.
Maybe leave and come back.
Yeah, I'll probably have to do that. Sorry about that.
Okay, no problem.
Can you hear me and see me?
Yes.
And do you see my screen again?
We do see your screen, so I think it's fine.
You see the PowerPoint presentation?
Yeah.
Okay. Okay, well, sorry about that.
No problem.
Where was I? I described the pictures of the...
Yeah, you were here.
I talked about, yes, okay, oceanic lithosphere. So continents survive for longer than oceans because essentially their density is lower than that of the mantle underneath. So they will always float on top of the mantle, whereas oceanic lithosphere doesn't really. Okay, so can we apply the same concept to Cratonic lithosphere? Unfortunately, it's a little bit more complex there. So first of all, we saw in the slide I showed you earlier that the seismic velocities illustrate that cratons are very thick, but they're not only thick, they're actually also much colder than normal lithosphere. And this is illustrated in the plot on the bottom left, where we have basically the age of lithosphere plotted against the surface heat flow. And what you can see is that the older lithosphere has lower heat flow than younger lithosphere. So Cratonic lithosphere, which is generally very old, has generally also a very low heat flow. So Cratonic lithospheres are thick and cold. You wouldn't expect them to actually, that wouldn't be the reason why they survive. Another interesting thing is to think about isostasy. So the reason why oceanic lithosphere is underwater and continents are above water is because the continents are less dense than the oceanic lithosphere. Hence, the oceanic lithosphere is submerging. So since normal continental lithosphere is sitting just above sea level, then you would expect that old and cold, thick cratons would actually be denser and therefore sink below sea level. But we know, of course, that's not the case. Most Protonic lithosphere is not underwater. So what is going on? Why is this the case? Well, Tom Jordan already recognized this in the 1970s, and he recognized that there must be something inside the lithosphere that makes it less dense than it appears to be by purely looking at temperature and surface heat flow. And he argued for the so-called Isopicnic Hypothesis. So he argued that the thermal negative buoyancy of Protonic lithosphere must be somehow offset by positive buoyancy. Now, the positive buoyancy is almost certainly chemical buoyancy. So the composition somewhere in the Craton must be such that the density becomes lower. Crustal thickness is an obvious candidate. So maybe the crust of Cratonic lithosphere is thicker than normal for continental lithosphere, and that would kind of offset then the negative density because of temperature. However, looking at the crustal thickness map, which I show here on the right-hand side, this is actually probably not working very well. So we can clearly see how oceanic lithosphere has this very thin crust of up to 7 or so kilometers, but the continental lithosphere has a crust that varies somewhere between 35 and 45 kilometers for most cases, but there isn't really a strong correlation with Cratonic lithosphere. So let me illustrate this further by taking one example, and this is an example of the Slave Craton here in northern Canada, the northern part of North America in Canada. And this is kind of a cross-section going from south to north, here from left to right. And in the south, we have the so-called Slave Craton, which has a very thick lithosphere, more than 250 kilometers, and a low heat flow, surface heat flow. And as you go further north, the lithosphere gets younger and it gets thinner. And it gets even thinner than 100 kilometers. So you would think from this decrease in thickness that the average density of the younger lithosphere would be significantly lower than that of older lithosphere, but and therefore it would sit higher, so in terms of isostasy. But the opposite is actually true. The Slave Craton is not underwater, so something else must be compensating that. And as you can see, the crustal thickness varies slightly, but this variation is by far not enough to explain the buoyancy of Cratonic lithosphere. So what Tom Jordan already suggested in the 70s was actually the chemical buoyancy, the compositional buoyancy is not so much in the crust, it must be in the mantle lithosphere underneath the crust. So the dark green area in this case. So he argued that the mantle lithosphere of Cratonic parts of the world must have a lower density. So then the question is, what causes this lower density? Well, the answer to that is almost certainly something related to mantle melting. So almost all mantle material throughout its long history probably underwent some form of melting, but some parts underwent more melting than others. And it's the degree of melting that will actually determine the density of mantle material as well. So this is kind of illustrated in the plot on the right. If you melt a mantle rock to a certain degree, the density will drop. So roughly for every 20% of melting, we get 1% of density decrease. Doesn't actually sound like a lot, 1 or 2%, but that's the same density decrease you would get by warming up mantle material by 500 or 1,000 degrees. And we know that that is responsible for a lot of mantle convection on the Earth. So it is probably relevant. Now, the reason why this density decrease is taking place is because during the melting process, the incompatible elements are left with the melt. And what is left behind, the residue, is then stripped of those incompatible elements. And one of those incompatible elements is iron. And iron is very dense. So any melting process takes away dense iron from the rock, and therefore the residue is going to be lighter. So is that the case for Protonic lithosphere? And if so, why is that the case? Well, it's actually not unlikely that Protonic lithosphere underwent more melting, because the temperatures in the early Earth were probably hotter than they are today. And in fact, observations show that the mantle temperatures in the Archean, or the early Archean, were probably somewhere between 150 and 250 degrees hotter than they are today. And a hotter mantle obviously leads to more melting. Can we see this in observations as well? Well, in fact, we can, by again looking at the compositions of the residue. And what we find is that the residue is stripped of iron, or in other words, this is usually measured in terms of the ratio of magnesium to iron. So by stripping mantle material of the iron, we're left with a relatively larger proportion of magnesium, which is typically referred to as the magnesium number. So a higher magnesium number means more melting. And in fact, all the Archean terrains, so the oldest terrains, have the largest magnesium number, so they underwent the largest degree of melting and therefore are the lightest. So that probably explains the fact why the reason why Cratonic lithosphere is rather neutrally buoyant. So it isn't as dense as you would expect it to be by purely looking at its low, by its cold temperatures. Now, interestingly, the other question you might ask is, why is it that Protonic lithosphere is so much thicker than other lithosphere? And the same melting process is probably responsible for that as well. So this needs a little bit of explanation. During the melting, it's not only the dense iron that's taken out, but it's also any other incompatible elements, including a lot of volatiles, and that includes water. Now, rocks. The strength of rocks is to a large degree depending on the amount of water that sits in the rock. Dry rocks are generally stronger than wet rocks. And this is kind of illustrated with a laboratory experiment that's shown here on the right. Larger concentrations of water, so more to the right, give you lower strain rates in laboratory experiments, which indicates stronger rocks. So why is this important? Well, the thickness of lithosphere is typically limited by the strength of the lithosphere. And this is probably most easily explained for oceanic lithosphere. As oceanic lithosphere forms at mid-ocean ridges, it's very thin, and then it starts to grow by thermal cooling. And we probably all have learned about this process in the past, and we can even derive an analytical half-space cooling solution for that. But that only works up to a certain point, and at some point the lithosphere at the base starts to form little instabilities, as you can see in this numerical calculation. And these instabilities lead to bursts of heat being introduced into the lithosphere from below, and that kind of slows down the cooling process of the lithosphere. And at some point the lithosphere doesn't cool any further at all. So and it also limits the thickness of the lithosphere. Now, the stronger the mantle lithosphere is, so the black part in this calculation, the stronger that material is, the more it resists those instabilities. So stronger rocks basically are able to cool for longer before those instabilities kick in. And if Cratonic lithosphere is indeed stronger because it did melt more, it's quite likely that it also will resist these instabilities and therefore is able to grow a lot thicker, apparently up to 200 to 300 kilometers thick. Okay, so summary of the first part. What is a Cratonic lithosphere? Well, it's essentially a piece of continental lithosphere that has not seen any significant tectonic activity for at least 1 billion years. Both Protonic crust and the underlying mantle lithosphere are typically very, very, very old. Cratons are typically thicker and colder than Phanerozoic lithosphere, but they do not have a thicker crust. So it's only the lithospheric thickness that's different, not so much the crustal thickness, but they are more buoyant and they're actually also stronger. Right. now we can move on to the second part of the talk, is how to build Protonic lithosphere. And this has been a popular topic for at least the last 2 decades or so, and there's been several proposed conceptual models that might be able to do it. And this paper by Sinti Lee in 2011 kind of gave a nice summary, although not all the proposed models since then fit these 3 categories, but they're still giving a nice overview. So first of all, we've got probably the simplest model that forms a craton in situ, essentially by just having a large burst of melting that would lead to significant depletion of part of the mantle that becomes then light and very strong and freezes into something that later on then becomes Protonic lithosphere. It's a very simple model conceptually, but the problem is that in order to form large amounts of melt down to depth of 200 or 300 kilometers or so, it requires extremely high temperatures. And even for the early Earth, these temperatures are probably not reached. Although probably some models need to be, some numerical models need to test this further. Another model that's probably now the most successful model, or the most popular model, I should say, is a model that is being shortened and thickened over time. So the idea is that if in the plate tectonic setting you would have a model, you have lithosphere that would be shortened by some form of underthrusting or imbrication, but it would probably also work in a non-plate tectonic setting, as I will show later on. And this is the kind of model that we decided to elaborate further, and I will show you some results of later on. And then, so this one of the reasons for the popularity of this model initially was the fact that these dipping features that you see in the conceptual model are actually also recognized in the rock record or through geophysical measurements, and they're recognized as dipping seismic reflectors, which are thought to be like well, ancient thrust planes or subduction zones. The final model is probably more uniformitarian in the sense that this is a model that proposed that protons formed back in the Archean more or less in the same way that we know that continental lithosphere is being formed today. This is mostly in subduction zones where you have continuous new melt being formed, and all this melt accumulates to form thick mountain ranges similar to, say, the Andes we form today. So those are the 3 models, and as I said, the most popular one is the shortening and thickening model, which I'm going to also elaborate on a bit further. So one of the additional pieces of evidence that this is perhaps the more likely model to occur is another observation, and that is that the mantle rocks that we find today in Protonic mantle lithosphere, we have access to them through kimberlites and xenoliths coming out of kimberlites. We know the depth where they're coming from, and we also know the temperature at which they're being emplaced at the moment in cratons. But from the composition of these rocks, we can also tell what was the pressure and temperature when these rocks were formed. And obviously the temperatures were significantly higher, but more interestingly, the pressures were lower. So these rocks were formed at higher temperatures with lower pressures than they are residing at today. So this suggests that somehow the lithosphere, all these rocks moved down to deeper levels, which suggests probably some form of thickening of the lithosphere. So this added to the popularity of this particular model setup. So what Hong Liang Wang worked on for his PhD was to test this model in a non-plate tectonic setting, because it's quite likely that many of these Archean terrains were formed when plate tectonics may not have been operating yet. I'll come back to that later on. So conceptually, the idea is you form lithosphere, which probably is depleted at the base already, then some form of tectonic shortening event takes place, which leads to the lithosphere being shortened and thickened over time. And then you could call that a craton, but really the only way that it becomes a successful craton that we can still observe today is that that scenario remains present, remains stable for then a long time, for billions of years afterwards, essentially. So that would be a successful model, but as I will show you, not all the models that we did are successful, and some of them just collapse because they become unstable or they show some gravitational collapse, and in that case, the craton formation scenario failed. So we did this using numerical models, and just to give you an idea of what goes into these numericals. I don't have time to really go into all the details of how the numerical models has been set up, but generally we do these calculations in a box as shown over here. In this case, we use an upper mantle box. So the box is kind of 660 kilometers deep and has an aspect ratio of roughly 1:4 or something like that. And what we want to solve for is how the material in this box is flowing around. So what we need is some equations that describe the flow. Now, flow of mantle material and of lithosphere on top of the mantle on long geological timescales can be described by the flow of a fluid. So basically, we treat the Earth as a very sticky fluid. Now, fluid dynamical equations are, for example, the Navier-Stokes equations, and those can be solved by taking into account conservation of mass and conservation of momentum. And those are the two equations shown over here, the top two equations. And in principle, that would be all that is needed. However, we know that particularly the flow of material depends on the strength of the material, and that is again a function of temperature. Also, the buoyancy or the density of material is a function of temperature. So we need to solve for temperature somehow as well. And that is solved then using the thermal energy equation. That is the third equation here given. We also want to track where compositions are going, for example, where crustal material is sitting or where mantle material is sitting. So we need to somehow solve for composition as well, which is the C in this equation. So we need to track composition, and that gives us a fourth equation. So we solve this set of equations simultaneously in a numerical model to understand how Protonic lithosphere can potentially be formed. Okay, the way that we addressed this problem was basically in two steps. First of all, we found out early on that a very important parameter in all of this is the strength of this mantle lithosphere. As I described earlier, we think that Protonic lithosphere is stronger than normal lithosphere, but how strong it really is not really all that clear. So, and since it's such an important parameter in the models that I'm going to show you, what Hong Liang did first was to look at, like, bracket the constraints of how strong mantle lithosphere has to be in order for it to survive for billions of years. So in the first set of models, he didn't actually build Protonic lithosphere, he just imposed it in the models. So we had a box, just like I showed you before, a box in which basically normal lithosphere was imposed, and right in the middle of the box, he built a thicker lithosphere, which is the Protonic lithosphere in the middle of the box. And then let mantle convection essentially attack that Protonic lithosphere for a few billion years and see if it survives for that long. Because if it doesn't survive, we probably are dealing with the wrong rheology, because we do know in real life, Protonic lithosphere is able to survive for billions of years. Now, to make a long story short, basically, we found, not surprisingly, that the mantle lithosphere needs to be strong in order to survive, but the factor of 50 stronger was sufficient to let it survive for several billions of years. So, keeping that constraint in mind, there's actually a lot more to say about these models, but I'm trying to move on a bit more quickly. He used that constraint to build a more complicated set of models in which he essentially use the same concept, the same box, but instead of imposing a Protonic lithosphere right in the middle, we try to build it in this case by shortening the lithosphere and see if it builds a Craton self-consistently. So this is a rather complicated slide, a bit of a busy slide, but the key features in these models is that we have a box where we impose some horizontal velocity that causes some shortening. Mantle temperatures are taken higher than what we know is suitable for today. Essentially, a 200-degree hotter mantle to represent the early Earth situation. We also have a higher radioactive heating. So we start off with a higher radioactive heating and that slowly decay over time. Also, the bottom boundary condition is set such that it leads to secular cooling, so slow cooling of the entire mantle over time. Using a complicated rheology, which is actually used quite often in most geodynamical models, using diffusion creep, dislocation creep, and plastic yielding. Using the depletion strengthening, which we just derived in the previous slide, and some buoyancy as well. Okay, now let's look at some first model calculation. I have a little animation to wake you up again. So what this calculation is showing, at the top we have the temperature field. So as you saw, we have a phase of shortening of the lithosphere. In this case, we have 500 kilometers of shortening done in 50 million years. So that's about 1 centimeter per year of shortening. And that leads to the formation of this Photonic lithosphere. Now, you can see that the rheologically strong part is shown here in blue. And now the interesting part of this is that after the shortening, we are not only able to maintain a Cratonic lithosphere that remains thick, but actually it seems to continue to thicken over time. It's a very slow process. I don't have time to run the video again, but on the right-hand side, I've got a few snapshots to look at of this video. So you see that the lithosphere slowly thickens over time as you continue the calculations. And after 1 or 2 billion years, we form a lithosphere that's well over 200 kilometers thick. So essentially what we have is a two-stage formation process of Cratonic lithosphere. First, we have some tectonic shortening that seems to trigger the formation of thick lithosphere. But then after that shortening, gravity seems to shorten the lithosphere further in a so-called, what is something that we refer to as gravitational self-thickening. This lithosphere is able to survive for billions of years afterwards. So this is what we refer to then as a relatively successful numerical model to create a Craton lithosphere. But as I said, not all the models are successful. And in a way, rather than trying to find one single model that seems to somehow reproduce the Earth, we were actually more interested in how sensitive these kind of models are to the different parameters to understand which are the important parameters here. So what we did is we varied several parameters here and reran the models to see whether it evolved differently. Now, I don't have time to go into all the variations that we did, so I'm just going to give you a few examples. One of them was that we varied the timing of the shortening. So as I explained before, we had 500 kilometers of shortening, which was achieved in 50 million years of 1 centimeter per year of shortening. Well, is that realistic? We don't really know. I mean, for today, 50 million years is probably not unrealistic for a typical tectonic event, but whether that is realistic for an early Earth event, we don't really know. We really are lacking any of the observations for that, I think. But what we tried is several scenarios, one in which we did no shortening at all, one we did a little bit of shortening, 30 million years, and one when we did even more shortening. And all compare that to the default calculation, which is the red line in here. So what we're looking at this plot here is basically the evolution of the plate thickness over time. So the models, they start on the left, where time is 0. Then we have we had 50 million years of thickening that immediately leads to to a Cratonic lithosphere that was about, what is it, 170, 180 kilometers thick. But then over time, we achieved this so-called gravitational self-thickening event that eventually led to a lithosphere that's more than 200 kilometers thick. Now, if we don't impose any shortening at all, then we apparently don't get any triggering for this gravitational self-thickening either. And therefore, we essentially end up with a lithosphere that is not thickening at all and therefore is not suitable. We wouldn't call this a Craton. 30 million years of shortening does something in between. The more interesting case is when we shorten it for longer than 50 million years. And that's the kind of yellow-orange line that you see here. It immediately forms a very thick Photonic lithosphere, which is not surprising, because we keep on shortening and thickening it until it's very, very thick. However, it's not stable. As you can see in this calculation, the thickness then decreases over time. So rather than self-thickening, it seems to get destroyed over time. What's happening in these calculations is that little instability, so convective instability, seem to happen at the edge of the lithosphere, and these tend to destroy the lithosphere. So this is a process to watch out for, because clearly Protonic lithosphere in reality doesn't really undergo this kind of shortening, or this destruction. Otherwise, we probably wouldn't observe it anymore after several billions of years. Another scenario we looked at is how fast would it deform? So we achieved 500 kilometers of shortening in 50 million years, but you can do it slower or faster. And again, we don't really know the rates of tectonic activity back in the Archean. We only have some idea of how it looks like today. For example, this is a map of strain rates across the Earth from GPS measurements, and all the colored areas have significant tectonic activity. The white areas basically don't have any internal deformation that is measurable. But interestingly, for example, in the Andes or in the Himalayas, we end up with strain rates, compressive strain rates on the order of 10 to the power -8 per year or so. And this is actually also the rate that we imposed for our default calculation that I showed you earlier. But we tried some faster and slower deformation, and the bottom line is that it doesn't really matter very much. So these results are robust with respect to the speed at which you deform these, this lithosphere. Finally, the final example I wanted to show you is the effect of secular cooling. So how fast do we cool the Earth? We know, of course, that the Earth was cooling over time from the Archean to today, but the exact rate of cooling isn't really very clear. So we tried different models, but again, to make a long story short, it doesn't really make that much difference how fast you deform, how fast you cool the mantle, because in all cases we were able to form this stable Cratonic lithosphere, except for one scenario where we didn't cool it at all, and then after, interestingly enough, it remained stable for at least 1 billion years, but then it started to show some instabilities. So perhaps this illustrates that we need some kind of cooling. If the Earth wouldn't have been cooling over time, maybe Cratons wouldn't have been stable. Right. So those are the kind of models I wanted to show, and that is the work that Hongli and Wang has been doing. But I mentioned also that I've been working with Charitra Jain more recently, and one of the projects that we tried to address there was to see if that tectonic shortening that we imposed in the models in the past, whether we can actually get that self-consistently as well. Obviously, in those numerical models, you can impose any kind of shortening you want, but whether these are naturally occurring is another matter. So in the models that Charitra did, we had a larger scale model. So in this case, we're dealing with, well, this is basically an entire mantle of 3,000 kilometers thick. So we can self-consistently model mantle convection and mantle plumes and so on. And on the left, we see composition. On the right, we see temperature. And what we see in those models is that we get convection, we get blobs of materials that sink into the mantle. We've got mantle plumes rising up. The reason I show you this particular model calculation is because at the surface, we see lithosphere being formed as these purple blobs here. And these purple bits, as you can see, they're slowly moving together. So this leads to shortening of the shortening and thickening of the lithosphere, similar to what we imposed on the numerical models in the smaller mental calculation. So this actually shows that imposing those tectonic strains isn't something that we made up. It's actually something that can happen naturally in mental convection calculations as well, even in the absence of plate tectonics. Okay, so that's basically all I wanted to say about these tectonic shortening models. But of course, there are other models being proposed. And the last few slides of my talk, I would like to briefly go into some of these other scenarios and whether they are successful or not. So you may remember that the first scenario, that the conceptual model that I proposed, was one where we have a big mantle plume that kind of creates a Protonic lithosphere in situ. So Hong Liang tried to do that as well in his calculations, using essentially the same numerical model setup, but instead of shortening it, he now imposed a large mantle plume. So a single large mantle plume event, which depletes the lithosphere, and see if that actually creates a Protonic lithosphere. The problem is that in this calculation, the mantle plume material spreads out along the entire lithosphere. So even though you probably form some kind of strong base, some strong root of the lithosphere actually never grows very thick in this concept. So it isn't able to grow any thicker than about 150 or so kilometers. So somehow we still then need some event that thickens this lithosphere to a thickness of 200 to 300 kilometers, which isn't clear how that would work in this particular scenario. Another model, this is work not by ourselves but by others, is trying to create Protonic lithosphere using different scenarios. So this is work by Fabio Capitanio from Monash University in Australia. He and his team, interestingly, they used a different scenario. Instead of shortening the lithosphere, what they did is they stretched the lithosphere. So the stretching in the lithosphere led to large amounts of decompression melting. And all that melting again strengthened the lithospheres, and they found some form of gravitational self-thickening as well in their models. So eventually they form Protonic lithosphere, with perhaps the only caveat is that the thickness of their lithospheres is up to about 150 kilometers or so, maybe a little bit deeper at places. But again, it isn't really clear how this lithosphere would form Protonic plates that are 200 to 300 kilometers thick. But other than that, it is actually quite an elegant model in the sense that they self-consistently form this strong mantle lithosphere. Okay, I mentioned before that all of the models that we show so far, and that includes the model by Fabio, these were models that did not include any plate tectonics. But the question is whether plate tectonics actually operated during the formation of cratons. So most cratons have an age somewhere between 3 and 2 billion years. So that kind of falls along the boundary between the Archean and the Proterozoic. Now, the plot on the bottom right here is from Palin and Santosh, a paper that was published last year, and they compiled from other papers when people have proposed that plate tectonics started, and most of them start around well, somewhere in the Archean. So it's not unlikely that at least some of the Protonic lithosphere that we see today were formed during a period when plate tectonics was probably already operating. Maybe not all, but some of them. And in that case, we have to look at scenarios where plate tectonics plays a role. So the imbrication model that I showed at the beginning of the talk is something that needs to be tried out. And this has been elaborated further in a paper by Régier from 2018. And it would be nice to try out this conceptual model using numerical tools as well. So a recent suggested methodology to form Cratonic lithosphere in the presence of plate tectonics was published by Perchuk and co-workers. And they argue that if plate tectonics took place, we have oceanic lithosphere, but oceanic lithosphere is rather thin. And in a hotter mantle, that probably leads to a lot of depleted mantle that sits below this thin oceanic lithosphere. So that would be the purple layer at the base of oceanic lithosphere. And as these oceanic lithosphere subducts and continents collide, we end up with this purple material that kind of can't go anywhere. It's buoyant material, it's depleted mantle material, and therefore it naturally resides at the base of the continental lithosphere. And over time, it then grows into a Cratonic lithosphere. So this is an alternative suggestion for how cratons could possibly have formed. So what are the next steps? Well, I think we have to just accept the fact that if we are looking at events that took place a long time ago, in this case, Craton formation taking place several billion years ago, we're always going to be short of observations. It's been suggested that Craton formation and Craton evolution and Craton destruction are all part of one process, and you can't really distinguish one from the other. And that could actually be a new avenue to go into, because Craton destruction is a process that has been studied quite a lot, particularly for the North China Craton. So there's lots of observational evidence that we might be able to use to also shed new lights on the formation of Cratons. Another thing that I mentioned before, we need to look at the formation of Cratons in the presence of plate tectonics, and I think there's more work to be done there as well. So that leads me to the conclusions of this talk, and that is that, well, first of all, Cratons are thick, stable terrains that formed either in the late Archean or the early Proterozoic, and have buoyant and strong mantle lithosphere. And our preferred way to form this Cratonic lithosphere is through a two-stage shortening and thickening model. So first, a tectonic shortening event that lasts only several tens of millions of years, but it is then followed by a gravitational self-thickening event that could last for several hundreds of years. Now, in order to keep the Craton stable, we need a certain amount, a minimum amount of shortening to trigger the event. And we also found that we need some form of cooling of the mantle to keep this process, to keep the Craton stable. And future directions could be to look into combined Craton formation and destruction models, and to incorporate plate tectonics in the modeling that we have done. And with that, I'll stop here, and I'm more than happy to take some questions if there's some time left.
Well, thank you very much, Jeroen. So anyone has any question?
Hello.
Yeah.
Yeah. So this is Pushpendu from India. So can I ask something?
Yeah, sure. Go ahead.
Yeah. So thank you, Professor, for a very nice presentation. So I am basically an analog modeler. So I don't have much experience in numerical modeling. So I have one main question regarding the modeling thing, because I have gone through many papers on numerical modeling, and when I see these papers, I always see that the people who are doing numerical modeling, they start with some homogeneous mantle. Okay, so suppose you are working on some numerical simulation of mantle dynamics, or you are trying to simulate what was actually happening before 2 billion years ago. And if we consider the mantle condition and at that time, so that time the mantle was not homogeneous as you are taking, as the people are taking, right? So if I consider the mantle as some heterogeneous material, because at that time there might be some recycling of crustal material into the mantle, so there must be some heterogeneity. And do you think that the process will remain same if we consider the mantle as heterogeneous material? And if we want to consider the mantle as heterogeneous material in numerical simulations, what are the difficulties we will face?
Oh, those are very interesting questions, actually. So you're right, of course. I mean, the mantle isn't homogeneous. There must be some kind of heterogeneity taking place, but what I think is that these heterogeneities will be on a relatively small scale. So suppose you would have sinking slabs going into the mantle, and they are cycling through the mantle for maybe 1 billion years or so. What they end up is being very they're going to be mixed in, almost like if you're trying to mix two dyes in a pot of paint. And over time, if you keep on mixing them, the streaks are getting smaller and smaller. So probably eventually you end up at heterogeneities that are on the length scale of, I don't know, meters, tens of meters, hundreds of meters, probably not hundreds of kilometers. So therefore, we typically end up with heterogeneity on a scale that is probably too small to model it. So you need some kind of parameterized approach to deal with that. And actually some models do this. To be honest, I haven't seen that for Craton formation models, but there are some models that deal with this heterogeneity by not advecting one material, but advecting several materials. And then, for example, consider the melting of each of those components separately. So that can be done, but I'm not quite sure. So the other part of your question, how much that would then influence the Craton formation process, I'm not actually quite sure how much that would influence the Craton process. It might obviously lead to different chemical compositions, but I think the scale is too small to affect the dynamics.
Okay. Thank you. And then I have one more question. So if we consider, and you have already shown that there are some Archean Craton that were formed after the plate tectonics, and some were formed before the starting of plate tectonics. So when we are studying them, so how do you consider that this one was formed after the plate tectonics began, and this was formed before the plate tectonics? So is it easy?
Well, to be honest, I don't think we really know, because it's we do know a lot about how we do know when these Cratonic lithospheres formed, but the main problem is that we don't really know when plate tectonics started. And there's a lot of uncertainty about this. I mean, some people believe the plate tectonics started way back in the Hadean, and that probably means that all Cratonic lithosphere formed while plate tectonics was already there. Whereas others argue that it didn't actually properly start until maybe somewhere in the Proterozoic. Or in that case, it's possible that maybe all Cratonic lithosphere was formed in the absence of plate tectonics. I know this is not a really satisfying answer, but I think we just have to consider that some of them formed with and some of them formed without plate tectonics, or even maybe the two are related. Maybe the onset of plate tectonics somehow influenced the formation of Cratons, or the other way around. In fact, one of the papers I showed you was the paper by Beale, and actually they consider that concept of that basically the timing of the onset of plate tectonics was the timing of large stresses occurring in the mantle that might have led to the formation of Cratonic lithosphere.
Okay. And one last question, Professor. That if what you have already said that in early Earth the mantle potential temperature was very high, right? In terms of 2 days condition, and it affects the viscosity of the mantle, right? So that means that the viscosity of the mantle was lesser than what it is today. So then how the so is there any relation between the low viscosity of mantle and the dripping of crustal things? So can we delete this thing?
Yeah, definitely. That's a very good question. So yes, the mantle was probably weaker. The mantle lithosphere was weaker in the sense that it was hotter and therefore it was weaker. Obviously, if it was more depleted for some reason, it was probably stronger again. But there is probably no reason to assume that. So it is likely that the mantle, the hot mantle underneath the lithosphere was weaker, while at the same time the mantle lithosphere, so the part of the mantle that belonged to the lithosphere, was stronger because it underwent more melting. So the contrast between the viscosity contrast between the mantle lithosphere and the underlying astenosphere was maybe significantly larger in the early Earth than it is today, because the mantle was weaker back then. The convecting mantle was weaker. Yes. Yeah.
Okay. Thank you, Professor. And probably I will send you an email regarding this some more questions, because in this conference we do not have much time. So yeah. Thank you for the presentation. I will contact you. Okay. Thank you.
Yeah, I'm more than happy to answer more questions by email.
Yeah. Please remember my name. This is Puspendu from India. Okay.
Thank you.
Welcome.
Okay. We have Professor Audia wanting to ask a question.
So, Jeroen, thank you very much for this very nice talk. So, on the modeling side, I mean, you're using a viscoplastic model, rheology, right? And I mean, getting back to my, well, I remember from the early papers of Yannick Ricard, whether the grain size, I mean, should have an effect, whether you're accounting for it. And also, I didn't understand, I mean, in such a modeling that in such a model that you're doing, how do you handle, I mean, are you putting an upper and the lower bound in your viscosities, and how do you handle these changes, very big changes within the viscosity? This is one point. And regarding the plume part, I mean, if we have to see it as a 3D or a 4D model, I think that a plume can basically either reduce the tectonic thickening, or it could maybe even give a certain long-term stability to the Craton. So I still do not understand. I mean, how do you relate the mantle plume to the Craton time lifespan?
Yeah. So yeah, good point. So first of all, about your comment on grain size evolution. So this is actually a very active field. And I must admit that the models that we have been doing did not consider grain size evolution. So essentially, depending on whether you're in diffusion or dislocation creep, in diffusion creep, grains tend to grow, and in dislocation creep, they tend to decrease again. And so, but that strongly affects the viscosity of material. So grain size evolution is probably something important. However, these models were already dealing with a lot of other complexities, and therefore grain size was kind of fixed in these models to a fixed number, which is obviously probably not realistic. In reality, it did vary, but we decided to not go there and not added complexity to it, to first understand the evolution of the mantle without that grain size evolution. But you're right, we probably should repeat these kind of calculations by adding grain size evolution. And again, this, as far as I'm aware, this has not really been looked at for Craton formation processes, but definitely the evolution of grain size is something that has been studied for other processes. So that's one thing. The other question was, your second question was about, I forgot now.
Not the plume.
That was on how you handle the very large variations within your viscosities.
The very large variation in viscosity. So first of all, it needs quite a good numerical solver to do this. But luckily, we've got a number of codes that can actually handle these very large viscosity contrasts of 7 or 8 orders of magnitude. So we need those. But we do indeed limit that. So we have a maximum viscosity in the model, which in these models is typically set to something like 10 to the power 24 or so, if I remember well. And then we have a lower limit as well, which is usually set, I forgot the details, but I think they were set to either 10 to the power 17 or 18. So even though in some cases, especially when melt is present, you could have an even weaker material, but it doesn't seem to affect the dynamics very much if you go beyond these bounds. So, and this is a normal way of doing this. You limit it because otherwise you end up with almost infinite viscosities, and clearly you can't, no numerical model would be able to handle this. And your final question about mantle plumes, you're right, actually, and to be honest, I only showed one model, and to be honest, we only did a very limited number of models just to kind of have a look at this. But it needs more investigation. So what is with looking at the formation of cratons with mantle plumes, then you have basically two competing effects. One of them is that when you have a mantle plume, you create a lot of melting, and the melting leads to strengthening of that material, as I explained earlier. So that would be, in a way, positive action, because that means the mantle lithosphere could freeze in situ. However, mantle plumes are also very hot, so the material is thermally very weak. And the two, these are two competing effects. And it looks like in all the models we've done so far, it's the thermal weakening of the plume that wins. So somehow the material doesn't end up being strong, it ends up being weak, and therefore it spreads out like a pancake underneath the lithosphere. And yes, these are two-dimensional models, but we actually tried this same scenario in 3D, and although the dynamics is slightly different, we still saw the same issue. It tends to spread out, so the thermal weakening from the high temperatures wins over the compositional strengthening due to the melt depletion.
Thank you, Jeroen. Thank you very much.
You're welcome.
Yeah, I just like to say, if you have plume and plate tectonics, then you probably have boundaries where plume cannot spread as much.
You mean if in the
mean like if you have a subduction zone, then you're limiting the amount of spreading your plume could
definitely
have.
So yeah, you need, so in general, what you would need in order for the plume model to work, you need something that limits the plume material from spreading out.
Yeah.
Yeah, and you're right, maybe subduction zones could do that, but we weren't considering that scenario. But yes, that could potentially work. Almost like a mold where you keep your material in until it freezes, and then stays in that shape. I'm not sure if that's possible in a real Earth, but we could probably build a numerical model that does it.
Yeah. Okay. Is there other question?
There is one.
Yeah, actually, I got a question. Thank you for the presentation. Can you hear me?
Yes.
Yes.
Yeah.
So you mentioned that Cratonic lithosphere is formed under relatively high temperature, low pressure conditions. Am I right? So,
sorry, the mantle lithosphere of cratons formed under high temperature, low pressure conditions.
So are we referencing to today's geothermal gradient, or do we have an approach for Archean geothermal gradient to say it?
Well, these were the conditions they formed in general. So these are the pressures and temperatures are not really determined by, we don't need to consider a certain geothermal gradient. We just get the pressures and the temperatures straight from the rock. So we don't have to consider a certain geothermal gradient. But in general, you have to keep in mind that even though if we think about the temperature change in the mantle change from maybe 1550 to 1350 degrees, that sounds like a lot, but essentially it's only 10% or so. So the geothermal gradient probably only changed by something like 10%. So I'm not sure if that would make a big difference, if you see what I mean.
Okay, thank you.
Thanks. You're muted, Jeroen.
Yeah, sorry. I was going to ask if there was other question. No. Okay, so I think we'll finish there, and again we're going to thank you a lot, Jeroen, for telling us about Cratons, and it was a very, very interesting talk. So I thank you very much. And I also thank all the participants to this seminar.
Yeah, and thank you very much for the
Thank you very much.
and apologies for the technical glitch halfway.
No problem. We are used to that in here. Okay, so thank you very much.
Okay, thank you very much. Bye-bye.
Bye. Bye, everyone.